Okay, so today we're going to look at the divergence and curl of the magnetic field. This is for the E&M class, Physics 340, and let me explain what we're talking about. So this is divergence and curl of B. Okay? So like we talked about before, think of a straight wire. Let's say that the current is going into the board like this. Then if you put your thumb in the direction of current flow, your fingers will, the thumb of your right hand, your fingers will wrap around the wire in the direction of the magnetic field. So get a different color. So you get these loops of magnetic field. If it's a long straight wire, these loops are concentric and they would go this way. So the field is like this. Okay, so that's B. All right. So what I'm going to do is you've seen this in Physics 2, but what I'll do is I will march around here with a little displacement vector ds. Okay. So here is ds, 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 and ds, ds. Okay. So I'm going around and I'm going to sum up this integral around the loop of b dot ds. Okay. So what's the angle between b and ds? The angle between b and ds is 0. So this just becomes equal to the integral around the loop of b ds. Okay? So if you take the integral around the loop of b ds, well, at a constant radius, let's look at this radius where I am. Okay. Call this radius r. All right. At a constant radius, I hope that we would all agree that the magnetic field, just by symmetry and so forth, that the magnetic field is not changing around that loop, okay, as far as the magnitude. So the magnitude of the field is constant, and you get B times the integral around the loop of ds. Okay? What's the integral around the loop of ds? Well, that's just equal to 2 pi r. Right? Okay? So this is equal to b times 2 pi r. All right? But we know what b is for a long straight wire. We already calculated b. We calculated that for a long straight wire at some distance r from the center of the wire. It's a thin wire, okay? That b for the long straight wire, b is equal to mu naught I over 2 pi r. Okay? Now, I'm going to substitute that into here, and you get the integral. I'll rewrite this. The integral around the closed loop of b dot ds is equal to mu naught I over 2 pi r times 2 pi r. Well, these cancel. And you get that the integral around the closed loop of b dot ds the integral around a closed loop of b dot ds is equal to mu naught I. And we say I enclosed in the loop. Okay? So that would be that would be the current enclosed in whatever loop that you choose to go around. Notice that it's independent of the distance you are from the center of the wire. Okay, now this is true for a long straight wire. This may not be true in general. We're going to look at a more general case where we can generalize this to different types of currents and currents that are not necessarily uniform like this and so forth. Okay? Remember that I enclosed is equal to J dot dA. Okay? That would be, if you're looking at a cross section of the wire, all right, that would be that vector, that little area vector that represents that cross section, and J is the current density. That's something in amps per square meter, or amps per square centimeter, or amps per square nanometer, or some such thing like that. It is the current per unit area, okay? So I enclosed is J dot dA. Now, let's look at that. So I'm going to make a substitution here that the integral of, well, I should, I enclosed, I made a little mistake. I enclosed is equal to the integral of J dot dA. That makes more sense. All right. So I'll substitute that into what we had previously, okay, because now we can use the curl. The curl of B all right, dot dA is equal to, this is here, is equal to mu naught times the integral of J dot dA. Okay. So this says that, this is Stokes' theorem. This says that the integrands are equal to one another with a factor of mu naught. So del cross B, or the curl of B, so the curl of B is equal to mu naught J. Okay. Now, that's for the long straight wire. So we're going to generalize this and prove it for some arbitrary shape, arbitrary current density. Okay. So we know from Biot-Savart that for a current, the magnetic field vector BR is equal to mu naught over 4 pi times the integral of J R prime cross R hat divided by script R squared d tau prime. Remember that we're integrating over the prime coordinates. So this R prime in the current density is related to the source. We're integrating over the source. This and this are related to the field, okay? So I want to look at first the divergence of the magnetic field based on Biot-Savart, okay? So the divergence of the field del dot B is equal to the integral. I'll take the derivative under, ooh, I left out the constants. Let me put those back in. Mu naught over 4 pi, okay, times the integral of del dot J cross, and I'm going to leave out the argument of the function here, J cross script R hat over script R squared d tau prime. So that's the same thing that I had before, except now I'm taking the divergence and I'll take it under the integral sign. This is the divergence of the field. I can do that because the integral depends on the source, okay? So I can have underneath the integral sign. Well, if you recall from some of the vector identities that we talked about, a long time ago, this is of the form del dot A cross B. Okay? So that has that form. We're going to use that. We're going to use the identity for this to calculate this integral. Okay, and I'll write it out. So del, let's see. Del cross A, oops. Oh, okay, just hang on for just a second on that. I skipped something, okay. This is easy. We can do this, okay. This is hang on for this, okay. This is, no, that's what I had. Okay, I got it. Del dot A cross B, that's equal to B dot del cross A plus, minus A dot del cross B. Okay? So this plays the role of A and this plays the role of B. So we have that del dot B is equal to mu naught over 4 pi times the integral of, and I'm going to replace the integrand here with this, times the integral of script r hat over script r squared dotted with del cross j, okay, minus j dot del cross script r hat over script r squared d tau prime. Okay? But let's look at this. This is a field operator. This is operating on the field, and this is a source. This is equal to 0. Okay? This will survive. This is a field operator operating on field variables dotted with the source current. Okay? So let's see if we can calculate that. So we have the integral of, so del dot B is equal to mu naught over 4 pi times the integral of, the minus will come outside, j dot del cross script r hat over script r squared d tau prime. Okay. Let's look at this. So del cross script r hat over script r squared, you get script r hat is equal to script r over, that script r as a vector over its magnitude, script r. So you have del cross script r vector over r cubed. Okay, because I replaced script r hat with script r, the vector, over the magnitude of script r. Okay, so we're going to look at this del cross, or the curl of script r over r cubed. All right, and you know that I don't have a lot of board. You know that I don't have a lot of board space, so I can't write all this out. Oh well, what can we do? Recall, script r, the vector, is equal to x minus x prime I hat. Oops, we don't use I hat, we use x hat. Okay. Plus y minus y prime y hat plus z minus z prime z hat. Okay? So if we take a look at this, so del cross script r vector over r cubed, you get, I'll do it this way, you get x hat, y hat, z hat, and then d dx, d dy, d dz. Okay, and then down here you have x minus x prime over script r cubed and y minus y prime over script r cubed. And I'll squeeze this in over here. Z minus z prime over, and those are not together, script r cubed, okay? And if you calculate this, you'll find that if you do the calculation, you get an x, you get a dy, a ddy, z, and you go on down the line like this, and this whole thing is equal to 0. Okay, I'm not going to do the calculation. I'll leave that up to you. But this is the way you could calculate, finding the determinant. This is the way you can calculate that cross product. And you can write it out, and you'll find that this is equal to 0. So this says that, going way back, we started with del dot B. This says that del dot B is equal to 0. You already knew that from physics 2. Think of it. This is the divergence of the magnetic field. You know that magnetic field vectors are always closed, or the magnetic field lines are always closed loops. Okay? So it's a divergence-less field. Okay? Let's look at the curl. So for the curl, okay, we have del cross B. We're going to do the same thing that we did with the divergence. We're going to take that cross product underneath the integral. That curl is acting on the field. This integral is over the source. This is del cross del cross B. It is del cross B, but we're substituting in here. Okay. J cross R script R hat over R script R squared d tau prime. Okay? So we're going to use another one of those vector identities to handle this cross of a cross. And I'll show you that. So one of our identities was del cross A cross B is equal to B dot del times A minus A dot del B plus A del dot B, okay, minus B del dot A. Okay, don't get confused. This is not the magnetic field. This is in general vector A and vector B. Kind of bad form, but that's the way I do. I'm going to make a substitution here in just a second and show you this identity. Okay? So now I'll use this and I'll substitute in for all of these. Okay? So we have that del cross J cross script r hat over script r squared is equal to script r hat over script r squared dot del acting on J minus J dot del acting on script r hat over script r squared plus J del dot script r hat over script r squared minus script r hat over script r squared times del dot J. Okay. So let's look at these terms. In this first term, this is acting on the field. This is a field or gradient, okay? You're acting on a source. This only depends on the prime coordinates. This depends on the unprime coordinates. In other words, this is the source, this is the field operator, 0. Same thing down here, del dot J for this one. This is a field operator, this is a source, this is 0. So the only thing that survives is this term and this term inside the integral. Okay? So I'll replace that. All right? So we get del cross B, that's what we're after, is equal to mu naught over 4 pi times the integral of J del dot script r hat over script r squared, okay, minus J dot del script r hat over script r squared d tau prime. Okay? You've seen this before. This is the divergence of the electric field. I mean, this is related to the divergence of the electric field for a point charge. This is equal to 4 pi times del cubed of script r. Okay, that's the Dirac delta function. This, I started to show you the calculation for this, and it just takes too long. It's a few lines. I really don't think it's worth it. This integrates to 0. If you want to see the derivation, you can take a look at it in Griffiths. All right, so we have this whole thing is equal to just this term, so this is equal to mu naught over 4 pi times the integral of J r prime 4 pi del cubed R minus R prime d tau prime. Okay? So what does the Dirac delta function do? It picks out the place where when J of R prime is equal to R, okay, you get 1. All right, or in this case, you get 4 pi. So this is equal to mu naught. The 4 pi's cancel. J of R. Yeah, that's it. Okay? And this is exactly what we had. This should be a vector. This is exactly what we had before. We had that, well, this is what we had before. We had mu naught J. Okay? So Ampere's law, this is Ampere's law, so-called, named after Ampere. Ampere's law is del, or the curl of B is equal to mu naught J. Okay? By Stokes' theorem, we saw this before, from Stokes' theorem, we have that the integral of del cross of the curl of B dotted with dA is equal to the integral around the loop of B dot dx. That's what I did before. That's equal to mu naught J times the integral of J dot dA. And J dot dA, J dot dA, okay, that integral is equal to I enclosed. Should have, or mu naught, well, J dot dA is equal to I enclosed, or the integral of J dot dA. Okay? So we have the same thing that we started with before. This is Ampere's law in differential form. In integral form, it's just what I wrote down previously. In integral form, it's the integral of B dot ds. That's around, Griffiths may use a dl, I don't know, and that equals mu naught I enclosed. Okay. So that's all I'm going to do today, and next time we will look at some examples of this and see how to use Ampere's law and working with the divergence and the curl of the magnetic field. So I'll see you guys later. Thanks a lot. Have a good evening.